Hello everyone. Today we are going to start with the next lecture on the design of floor system. So in the previous lecture we have seen the design of the slab, two-way continuous slab, and also we have seen the design of a beam B2 and B3. So in this lecture we will go for the design of the beam B4. So now as you can see here in this the floor system, so we have designed B2 and B3. So B4 beam is remaining. So in this lecture we'll see how to design the beam B4. So we already know how the load distribution of the slab on the beam takes place. In the previous lecture I've explained you. The shorter span we have triangular loading, and on the longer span we have trapezoidal loading. And for triangular span the UDL is given by WU into L effective by 3, and for trapezoidal it is given by W into L effective by 2 into 1 minus 1 upon 3 into beta square, where beta is Ly by Lx. So now let us see. Here we can see the beam B4. If you can see my pointer, so the B4 is single beam which is resting on the exterior supports column, and the span of the beam is 7 meters. So this is 3.5 and this is 3.5, so the total span of the beam is 7 meters. And one more thing, this beam B3 is resting on beam B4. Okay, so now let us see the design of the beam B4. So first we will have to find out the dimensions of the beam. So let us consider the depth of the beam from the relation span by 10. So span is 7 meters, I have just mentioned you. So it is 700 mm. So let us assume the depth of the beam as 750 mm. So we always assume the depth of the beam or the dimensions on the higher side, so that the design comes safe. Okay, so let us select the size of the beam as 300 by 750 mm. So the first step is to find out the loads which is acting on the beam. So the load from the slab is given by WL by 3. As we have seen, triangular loading is given by WL by 3. So as here you can see, this this triangular load will be on the beam B4. So W into L by 3, W we have already found out in the design of the slab, that is 10.1875 into 3.5 by 3. So we got it as 12.468. Similarly, we'll find out the wall load. Wall load also I have mentioned how to find out its thickness into height into density, and again we have multiplied with the factor of safety 1.5, so it is 22.08. Similarly, self weight of the beam is 0.3, dimensions, cross sectional dimensions into density, 0.3 into 0.75 into density into factor of safety 1.5, so 8.4375. So the total factored load is 42.98. So let us approximate it to 43 kilonewton. So we got the total factored load on the beam. And also one more thing, as I mentioned you, this I have shown the load distribution in this figure. You can see the triangular loading is acting on the beam B4. And one more thing, this the point load from B3 is acting on B4. So the point load which is acting is 70.85 kilonewton. So if you have seen in the previous lecture that the shear force at the end for the beam B3 is 70.85, so that becomes our point load which is acting on the beam. So I hope that is clear how 70.85 kilonewton came. So it is the shear force on the beam B3. So this is how your diagram will look like. So the second step is to find out the shear force and the bending moment diagram. So this is the total span is 7 meters, and a point load is acting at the center 3.5 meter. This is 3.5, and this point load is from beam B3, which is 70.85 kilonewton, and the total UDL on the beam is 43 kilonewton per meter. So now it's a simply supported beam. You just have to find out the shear force and bending moment diagram. So now here one thing, a very important thing you need to pay attention is, so here you can see that the beam B4, okay, the beam B4 is actually resting on the columns. So these are the supports. So now there is a question that it is acting as a continuous beam, but you have to remember one thing. If you want to analyze this beam, you can analyze this beam as a simply supported beam. Okay, so whenever the behavior of the structure is as per the detailing which you provide. So for this we will consider, for simplicity and for convenience, we'll consider it as a simply supported beam, and we are going to design it as a simply supported beam, and accordingly we'll give the detailing. So remember one thing, the structure always behaves as per the detailing which you have done. Okay, so I hope I have made this very clear. Now, so we'll find out the shear force diagram and the bending moment diagram. So shear force, you can find out the reactions, and then you can find out the bending moment diagram is, you can directly find out WL square by 8 for UDL and WL by 4 for the point load, which is 387.3625. So we got the shear force also and the bending moment diagram also. So now for the calculation of the reinforcement, this is the formula. MR of a singly reinforced balance section is 0.138 FCK BD square. So the MR of a singly reinforced MR is given by the capacity of the section is 405 kilonewton meter and the moment which is acting is 387. So hence it is a singly reinforced section. It will be designed as a singly reinforced section. So this step we are doing just for checking whether it is singly or doubly reinforced section. So now we'll find out AST required. AST required, you already know the formula, 0.5 FCK BD upon Fy into 1 minus under root 1 minus 0.46 into mu upon FCK BD square. So this we got it as 1884.25 mm square. So we will also check this with your minimum steel. Your minimum steel is given by 0.85 BD upon Fy. So this is 430. So AST required is more than minimum steel. So we will consider the AST required. So now let us provide the suitable diameter and the number of bars. So let us provide, you can either provide 2 bars of 32 and 1 bar of 20, or you can also provide 2 bars of 25 and 2 bars of 25, that is 4 bars of 25 mm diameter. So for this 2 bars of 32 and 1 bar of 20, the area, the AST provided is 1922.65 mm square. So similarly you have to find out the percentage of the reinforcement. So the percentage of the reinforcement is nothing but AST upon BD into 100. So AST upon BD into 100 is 0.915 percentage. So the next step is to find out the shear reinforcement. So let us see, the shear force is nothing but 185.925. Okay, so the shear force is 185. Now tau V is given by VU upon BD. VU you know, B and D you know, so it is 0.885. For PT 0.915 percentage and M20 grade of concrete, tau C from page 73 table 19, you will get it as, by interpolating you will get it as 0.6 MPa. So we have to check tau V and tau C. So here tau V is greater than tau C, so hence shear reinforcement is required. So the shear reinforcement is required for the shear strength of VU minus tau C into BD. So where VU is 185 and tau C and B and D you know. So VUS is 59.925 kilonewton. VUS means this is the shear force for which we actually have to provide the shear reinforcement. So this is that actual force, that is VUS 59 kilonewton. So now let us select a suitable diameter and the number of legs. So assuming two-legged 8 mm diameter vertical stirrups, we'll find out the spacing. So the spacing is given by 0.87 Fy into ASV into D upon VUS, where ASV is two-legged 8 mm diameter, 2 into pi by 4 into 8 square. So we get it as 424. Similarly, the second condition is 0.87 Fy into ASV upon 0.4b. So we get it as 302. Third is 0.75 into D and 300. So we have to select the least of these four values. So let us provide two-legged 8 mm tall vertical stirrups at 300 mm center to center. So now we have designed the beam for shear also. So the last step is, which is to check for deflection. So we have already done this in the previous lecture. Check for deflection, you have to find out Fs, which is nothing but 0.58 Fy into AST required upon AST provided. So AST required is 1884 and provided is 1922. So we got this Fs value as 235. Similarly PT we have already found out, that is 0.915. Okay, so we got the check for deflection. So the next step is nothing but you have to, from the graph you have to check. Okay, so the value of MFT will be 1.1. so then you have to check the depth. So the depth will be around 318 mm. So this 318 mm is less than 700 mm, so hence it is safe. So this, the remaining step you can do it on your own. So the check for deflection is also satisfied. So now the last step is the reinforcement detailing. So let us see the reinforcement detailing. very important step. So this is B4 300 by 750 and the span is 7 meters. So first let us see the steel which we have got. So it is 2 bars of 32 or 1 bar of 20. I have also mentioned you can either provide two, I have also given you an alternative, you can provide 4 bars of 25 in 2 layers. So that's what I have shown here. So in one layer 2 bars of 25 and in the second layer 2 bars of 25, and at the top compressive steel is not required, it's a singly reinforced section. So at the top you can provide, just for anchor bars you can either provide 2 bars of 8 mm or 2 bars of 10 mm. So we'll provide 2 bars of 10 mm diameter. Okay, so the shear reinforcement is two-legged 8 mm at 300 center to center. So two-legged 8 tall at 300 center to center is the shear reinforcement, and this is the reinforcement detailing of your beam. I hope this is very much clear to you. So we have so far designed the slab, two-way continuous slab, and also we have designed a continuous beam and also this single span beam. So we have done the design of this floor system. Now the last step is remaining, that is the reinforcement detailing of the slab. So I will take that in the next lecture and I will show you how to do the reinforcement detailing of a two-way continuous slab. Okay, so I hope this is clear. And one more thing, as I've just mentioned you, this beam you can take it as a simply supported beam and accordingly you can design. Okay, so thank you.